This one's about as goofy as it gets. A key component of this kind of schematic is it's intended to show purpose, not electrical flow. Okay, so in the diagrams that are provided in these schematics, they often don't show the power source, the ground, or other elements of the circuit. They often won't show the load. Typically what they're going to show is the decisions being made by the shape of the objects put in place. And then within each of the objects or object groupings, you end up having some degree of decision making occurring. And I'm not going to get too deep into this other than superficially. I'll cover it over a few slides because you cover it far more deeply in digital logic and fire protection. But from the lens of schematics, they sort of are going to be a little bit more brief. However, they will show a pattern of decision making based upon an input versus an output. So a simple example of what a logic circuit can do, the more complex one is your computers, your iPhones, etc. But a simple version of one is, now that most of you guys have had a chance to play with most, not all of you, have had the chance to play with the generator test stand, you might remember the little switch that changes the amount of load that you can put on the system. And then there's a series of lights that light up. I actually made that light circuit and the logic circuit that drives it. But what that circuit, or what's happening is, the idea was they didn't want to make a whole bunch of switches and a whole bunch of, going this way and that. They also wanted to have something that if I went down one time, it would turn all the loads off. Okay, or take it back to just the lightest load. So inside there's 7 banks of resistors. They're actually big coils of wires that can, absorb several hundred amps of current being put out by the generator. Each one is successively stronger, but what they realize is rather than just have 7 different options, within 7 different banks I could have different combinations. So they used a binary form. So when I click the switch one time, I can turn on the first bank. When I click the switch the second time, I'll turn off the first bank and turn on the second bank. When I click the switch the third time, I'll turn on the first bank and the second bank. Okay, I'm now up to 11 binary. Okay, when I flip the switch again, I'll turn off the first 2 banks and turn on the third bank. When I flip it again, I'll now turn on the 1 again. I'm back to 101. And I can keep doing that and get, in this case now with 7 units and 0, 255 possibilities of load being an 8-bit register. Well, that's way more than we need. But on the other hand, it was, for the designers of this product, it was easy to buy an 8-bit register that's a bunch of these little logic gates glued together in a single chip. Use that to drive a bunch of relays, and then the big power relays are what turn the banks on and off. And meanwhile, it was programmed that if you do one set this way, it shuts them all off. Okay, so that was a simple use based upon readily available chips that allowed them to, they didn't have to program anything. They just bought the chip that has that general, it's an 8-bit binary counter. Okay. So the purpose of this kind of schematic is really more to show the general decision making and layout. And it's not that different than this high level schematic we saw that shows basic power distribution in the building. Okay? It's not intended to show individual wires at all. It's just intended to show some basic architecture. In this case, the basic decision-making architecture. Oftentimes, you're not going to necessarily need to know how to diagnose inside one of these circuits because in most of these combined components, there are no user serviceable parts. Yeah, if you really know what you're doing, you can look up the chip, order one from TI, or Mauser or whoever and pop a new one in there, and you figured it out, made it grand. But most of the time, that's sort of not the way it's going to play out. And of course, it's a programmable chip. You can buy the chip, but you don't know what the program was. Somebody, whoever made the entire system, put the program in it. So, however, having some knowledge about how this works allows you to identify, is it the computer? Is it the output transistor? Is it the load? Is it the wires in between? Is it the power source? For which all of those components very likely can be bought. Is it one of the sensors getting not providing appropriate data? So there's a whole bunch of building blocks. Essentially, a decision says, if this and that, then my output goes one way. Another one is either this or that. I could also have an exclusive either or. So it's either this or that, but not both and not neither. Okay. Another common one is I can have something that inverts the signal. So when a high comes in, a low comes out. I can also have a device that just isolates the two, commonly called a buffer. Actually, we end up using the exact same thing, just the non-inverting side of an inverter. What we're doing there is we're saying, okay, I've got some kind of an analog voltage that tends to wander a little bit. Maybe it goes from 5 to 7 volts somewhere, or 4 to 7 volts, and that's my high state. And my low state is usually half a volt up to 2.5 volts. Okay, I feed that into the buffer and then set the buffer threshold where anything above 3 volts, we're going to call the output a high, and anything below 3 volts, we're going to call the output a low, and it'll be 0 volts. And the output may be different. Maybe the output's only 2 volts. Okay, so the buffer sort of isolates the circuit, using the circuit to isolate the decision making. So whatever's happening here is the decision basis, but on the output side, you're going to either get 0 or 2. And that's it. Okay. Operational amplifier are devices that allow you to take an input and amplify it, take an input and feed the input back into, or take some of the output, feed it back into the input and amplify it even more. There's a whole bunch of different things you can do. And so note that while these are drawn somewhat schematically, there's some inputs and an output. They don't show the positive and negative to it. And you can have a decision system of a whole bunch of all of these all combined together into one little integrated chip. Okay. In which case, the diagram for the chip might be entirely different. So the diagram for an op-amp chip might have 10 op-amps in it, or 4 op-amps, or something like that. And but if you go look at the logic chart for that chip, which will also be in the specs data, it'll show 4 individual op-amps. Okay. Now, in this particular one, most of these are going to be multi-pin, either 8-pin, 16-pin, or a whole variety of different. Sometimes they have 10-pin. There's a few 4-pin, but most of the time, if they put multiple units into a single package, and if you don't need it, it's still soldered down, but the trace doesn't go anywhere. It doesn't do anything. They may be socket mounted, where you solder a socket in, and the socket, and then the chip goes into a socket, or by wave wash technology, they may, or by solder wave technology, they may do other means of surface mounting them. This one actually shows a buffer inverter. Get the triangle form that shows you what the logic values are. This shows all the different transistors, resistors, and other components that are used to make the decisions for input versus output. And if you look at the little arrows, you can sort of work out NPN, 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 PNP, I can't quite see, but I think that's a PNP. And it's a little fuzzy there. It's a little hard to see which way the arrow's going. But ultimately, the idea here is the top one, if a negative goes in, the output will be high. Or if a low goes in, the output will be high. If a high goes in, the output will be low. So it inverts the signal, it reverses it. On the lower side, it's called the non-inverting input. That input, if you use it by itself, the unit acts as a buffer. On the other hand, if you use the non-inverting input to set a threshold, you can then use it to set the threshold voltage by which the inverting voltage then makes its decision, the output makes its decision to flip based upon the input. So you can use this to set whatever that value is. You know, anything above 2 and anything below 2. And again, I'm not going to test you on any of this. I just want you to have a clear sense that the logic chart doesn't show you all of the electrical schematic behind the scenes. And usually when you look at the logic behind the scenes, you go, wow, okay. It's actually, I have kind of fun. I'm a geek, so I have a little bit of fun trying to figure out mentally how that thing works. But in use, all I really care about is power ground and what are the decision options, what's the possible available information that's going to go in, and what are the appropriate decision options coming out based on that information going in. Okay? But if I'm looking at the inverter, I take my oscilloscope, 2 different traces, and throw it on there. One signal should read the inverse of the other. If I'm not getting that, inputs, outputs, device in the middle. One of the 3 is bad, or the power supply. In this one, I just showed you a couple of pictures of the device that actually does wave soldering for a lot of your surface mount technology. This is actually through mount technology. What they do, this sort of silvery area here, this area, that all silver, that's molten solder. It's molten solder that's flowing up in here in a wave that comes out. And that wave is very carefully controlled. And so the solder boards move along a platform, moving their way along, and they just sweep right across that wave of solder sitting there, dip into it just enough to solder everything. If flux is needed, they're already pre-fluxed. And note that that wave of solder is staying nice and clear and shiny. It's not oxidizing at all. Well, if you look in here, that's because we've got it in an environmental chamber. Okay? And so what may be happening is, this isn't connected to the rest of the manufacturing process, but it comes into here through a little induction chamber. It's a little atmospheric gate that allows each board to come in, moves into the atmosphere controlled environment. That first section might actually be a preheat chamber. So they might, depending on the nature of the board, they might preheat larger components. There's a few larger components. They might preheat them some with a blast of hot air as it's moving along. Or they'll preheat the whole board to reduce the potential for cold solder joints. And then as the board moves across the solder wave, it then gets flow soldered or wave soldered, and then comes out of it, goes through a cooling process, and then ejects out the other end. So up here, this may be usually again they pre-flux it. So flushing may either remove anything that isn't pre-flux, or they can use a silkscreen template to where the flushing comes up and everything that is supposed to be fluxed has a certain type of silkscreen surface, and this flushing flux sticks to it, and everything else it just washes right back off. So there's a variety of different techniques there. To me, though, it's kind of cool to see the silver wave of molten solder flowing. And, gotta know the guys that thought all this stuff up, and then built one and it didn't work and tweaked it and built it, tweaked it, and he kept working on it, getting it better and better. They invested a lot of time and effort into it. Okay, wires, and in particular connectors. Connectors are our friend, much like volt drop checks. The voltmeter is our friend. Both of them make us lots of money. Okay? Now, the preponderance of electrical problems are at or very near the connector. So that's one reason they're our friend. But the other reason they're our friend is they provide us locations to do relatively easy testing from. So I can just connect a connector here and a connector there and a connector there and start testing from each of those locations to isolate down to a much narrower part of the schematic where my problem might be. Again, with the understanding that there's only 3 possible problems that can occur. Short, open, failed power source. Right? Of course, as luck would have it, the problem we're going to have is going to be right smack dab in the middle of this big, huge bundle. You know? That's kind of a nightmare. It looks like the belly of an airplane to me. I don't remember where I got that picture. It looks like the belly of an airplane, but boy, bundles that big sort of violates your redundancy sense. So I'm not quite sure what that's in, but I will say that if any one of those harnesses takes a hit, mechanical hit of some kind, a whole lot of systems could get taken offline. Okay. So the FAA, in their infinite wisdom, has decided that electrical wiring problems are the root of all evil, and you guys aren't competent to solve any of them. In fact, even the engineers and industry just isn't there competent to solve any of them. So they ran around the country and found a few pictures of some egregious things, which were pretty egregious. They made this big, huge PowerPoint. I actually, given how long, I've done a little bit of homework, and given how long this little fiefdom has been in existence, it became a very, very solid entity within the FAA right about the time. You remember a while back, quite a while back, Southwest Air got violated on some wire lacing issues that were absolutely pointless and ridiculous. My guess is that was orchestrated by this new fiefdom as a justification for being in existence. So they came out with this whole electrical wiring interconnect system. And they've got some big, huge manuals. They've got about a 300-frame PowerPoint, which I think this is the link to, much of which is painfully obvious stuff. However, within there, they do have some pictures of people doing really stupid stuff. So I think from your perspective, I don't dive too deep into it other than, several people saying, well, we really got to, cover this heavily. There's nothing in there that isn't already covered in the information we're already talking about. On the other hand, if you want to go work for the airlines, Delta, whoever, it would behoove you to go look into the PowerPoint, get some of the buzzwords, get up to speed on some of the buzzwords. That way when you go to interview, oh yeah, e-whiz, I do that every time I get up in the morning. I mean, no, it's to do with wiring, electrical wiring interconnection system, yeah, you need to be able, if you can pull that out, it might help you. Yeah, I just, Okay, so how many engineers are there on planet Earth? Multiply that number by 10, and that will give you the number of different connectors that are out there. It's crazy. Well, part of it is because, when we, in the next couple of slides, you talk about some of the manufacturers. If I call it Canon Connector Factory and say, hey, look, I want to build 10 million units. They're going to say, let me grab a pencil here and okay, what do you want? And they don't really care. They'll come up with 10 million units. They'll come up with, we're there. Okay, so the military comes along and says, well, we want something that is so bulletproof, no matter how badly we train our people, they will not be able to screw it up. But if the enemy captures it, they can't use it for anything. Okay, they can't connect it to any possible thing else. Right? So they'll make, but then they'll order 10 million units. Now, of course, they only needed 5 of the things. Right? So now they've got, 10 million minus 5 units, so they're going to try and use them elsewhere. And so they buy a bunch of stuff from Lycoming or someone else, and they say, oh, by the way, we've got all these connectors. We want you to use these connectors because we've got them all. And that's the kind of stuff the big players do. So you do end up seeing with some stuff that's a little obscure, where you've got a multi-pin, 27-pin connector where 7 of the pins are used. But in general, what we will do is, and again, they come in all kinds of forms: metal, plastic, stainless steel, aluminum, nylon, positive locking, some kind of clip, on and on and on. So when we're building up a wiring harness, what we'll do is we'll set up, we'll first design. We'll get dimensional parameters from the builder of the airframe, the automobile, or whatever, and we'll get some basic length dimensions for all the components and the runs. We'll then lay that out on a board and somewhat design what the harness needs to look like and where the wires are going to go. Once we do that, we'll then go on to a layup board and take all of the vehicle connectors and bolt them in various places so that you get the basic dimensions laid out. You'll then also see a number of pins and other supporting things. Meanwhile, over here, we're going to program into a wire identification cutting machine all the different wires I need. Okay, you turn that on, boom, it starts spitting out wires, pre-trimmed, all labeled, spits a bunch out. Pull that off, set it on a rack, get the next wire, set it on a rack, so you get a whole rack for all these different wires. While that's happening, somebody's job is then to pick up each wire and lay it out, put all the heat shrink in, do all the stuff, sort of clamp it in place, and then once all the wires are laid in place, somebody then comes back and fastidiously goes through and does all the connectors. It makes all the connectors at the appropriate length. The cost of that oftentimes is more expensive than the cost of the rest of the vehicle if you want to replace that part. I can tell you that's for certain that's true in the automobile industry. Typically, the cost of the value of a used vehicle, one of the major subsystem wiring harnesses to buy that new is probably more expensive than the cost of the entire vehicle. Having run into that numerous times. Basically, you build the vehicle, you paint it before installing anything else, you put that in. So just the cost of getting it in and out is going to be intense. Not to mention the cost of this part, not to mention the cost of all the darn things it connects to. This sort of goes back to the notion, has it been submerged? Everything's probably bad. It can look perfect and everything's bad. The other notion, which if you go out to Davis-Monthan out there a little bit west, east of Tucson, you'll see a bunch of perfectly brand spanking new airplanes sitting out there, doing nothing. Because they built them all, flew them out for a little while. And then after a while figured out that the insulation, that they built them all, insulation had a tendency that if you were running current through it and it got a little bit hot, it would kind of burn like primer cord. It was actually very, very flammable, which they didn't know. It's not flammable, it works great as long as it's not being subjected to a lot of current. But if there's an intense magnetic field around it, it becomes extremely flammable. There's nothing they could do. The cost of rewiring each of those airplanes was way, way more than the value of the airplane.
When they're creating a harness like that, testing it, do they pin it out or do they have a module that they plug it into that tests it?
I think it's going to depend on what they're doing. you know, if I'm throwing out one F-14 a month, probably not so much. If I'm throwing out one Boeing 737 a day, which I think is probably the max that Boeing is doing now. They're turning them out a lot. But yeah, they may have automated a lot of that to where, you know, each one of those connectors actually goes to a computer interface, and the computer has a bazillion little relays. And once it's all done, they go hit go, and it goes and does it all. Test voltage ohm, drop everything on the entire circuit, and then says, you're good to go, or go over to that connector. You screwed up and hooked it up backwards.
Do they environmental test it as well? Or?
Good question. If it's necessary, yeah. You would think they ought to. Again, that's going to be a function of their QA process as defined within their production certificate. So my guess is if it's needed, yes, they do it. So a really good connection is one that obviously provides continuity with limited resistance. Now, we know everything has resistance. We also know that we're going to take a bunch of copper and draw it out into a bunch of very thin strands of wire and twirl it all up to make wire out of it. Then we're going to take a different piece of copper and forge it into this weird connector that we then roll around. So the way it gets made is very different. So it's probably not the exact same kind of copper. It's a different alloy. Now, we may tin plate it, or we may gold plate it, or we may do other things to it. And we're going to put it all together, and then we're going to shove it into another connector that may be the same or may not. But at the end of the day, I'm going to have a variety of different metals here and different alloys. So the mere fact that we broke the wire and put a connector there is going to add some resistance that wouldn't have been there if the wire was just a straight wire going through. So we're going to reduce that as much as possible. We're going to make it mechanically sound and as unlikely as possible to break the wire during normal use. Okay? The normal use is going to include some relative motion. I've seen some like that big fat wire there. Probably doesn't have a lot of relative motion. But I'll bet you the vibration of turbine engines nearby going, whoa, there's some micro vibrations even moving through that. So I want to make sure that my connector does a pretty good job of supporting the wires and maintaining an electrical connection. Okay? If it needs to deal with environmental issues to prevent corrosion, it's going to have to do that. Okay? It should be, at this last one is where GM should be like run out of the United States and put on a small island for them. It should be easily disconnectable, but unable to disconnect without some positive action on the part of you, the technician. I have to say, some of the GM connectors, oh my Lord, you flex the tab, won't come off. Rip the tab off, won't come off. Pry on it, break the sensor in half, manually tear the sensor out of it, it won't let go. Same thing with a number of manufacturers that make spark plug leads. Man, that rubber boot gets on there, it is not going to come off without destroying the lead. Oh dear, buy another $80 harness. Right? So we don't suffer that well in aviation. In aviation, we're paying a lot of money for a connector. It damn well better work right. And so the players in aviation realize they've got expectations. Because the last thing in the world they need to find out is John Q or Jane Q mechanic connected and disconnected a few times, and it was such a bad connector that the process of connecting and disconnecting caused the wires to fail or the pins to fail, and at some point pin pushback happened and everybody died. Okay, that everybody died now, well, it was a bad connector. It doesn't even have to be entirely true. All I have to do is be a good enough lawyer to go in there and convince 12 people that it was a terrible connector and that big bad evil electrical connector manufacturer just did a shortcut and did an end run, and man, they're bad and evil. And suddenly you know, this lawsuit goes down. So, so yeah, Canon, AMP, Molex, big players. You know, IBM level players. I mean, major international concerns that you know, happily will take on any vendor or you know, any individual looking for a special kind of vendors. Pretty universally, we have male and female pin arrangements. There's sort of one exception to that where we sort of have these spring pads that come together and push. There, it's a little hard to say. Maybe the springy part is male and the pad part is female. There's sort of nothing going inside something. But in general, most of the time, connectors are tend to be male and female arrangements. The gender always is reflected by the pin, not by the connector. So in this particular case, you can see there's a male connector that fits inside a female housing. But it's the male pins here that go into the female. And the females in general are far more protected than the male. Okay? So note, here's a couple of examples in the world of computers. Molex, in most of theirs, they tend to do square corner and a sharp corner like a little boat. Here the square is on this side and the chamfered corners are on that side so that the connector is indexed. It can only go in one way. Most connector strategies call for it to be indexed so it can only go in one way. That's not universal, but most of the time they do. So because of this pin gender orientation, you want to protect, you want the side that needs the most protection to be in the most protected side. So the one thing I don't want is a dead short across power to ground. So I want to make sure that power and ground is located in the side of the connector to where if the connector is disconnected, it's really hard for something to short those two together. It can't just fall on something and short the two together. So if I put that on the female side, something actually has to dive into the two correct holes before a short will happen. Whereas if it's on this side, man, any bolt or nut or anything coming into there can very easily short a couple of critical leads, and then you know you're somewhat in trouble. Now that's not universal. Like that big fat wire we saw in the initial picture there, I could have a big huge connector where, in a number of cases, my load is on this side and power source is on that side, and then in other connections it's reversed. So this isn't a universal mandated strategy in Part 23 or anything like that, but it's generally a good philosophy, and as such, manufacturers often follow that. Okay, hopefully that makes a lot of sense. They do, typically these connectors are most often tin plated. Copper that's tin plated, a little bit of tin. Tin doesn't, it does oxidize over a long period of time. But tin with a very slight amount of lead in it does a pretty good job of being non-corrosive. It isn't perfect. It turns out that gold sort of thumbs its nose up at oxygen. Turns out there's no possible way that gold and oxygen can combine molecularly. Not without a whole lot of effort. So it can't corrode, because oxidization is corrosion with respect to metal. Okay? Gold can't chemically combine with oxygen, so it can't corrode. Well, that's pretty useful stuff. That's why it sits, in the sunken treasure ship at the bottom of the ocean indefinitely. Okay, the ship's long since gone, but boy, that pile of gold is still there. Or at least we think it is, right? So it turns out that gold has got another cool feature. Not only is it very ductile and you can pound it out really, really thin or paint it in very, very super thin microscopic layers, but it turns out that you can take certain alloys and add a very, very small amount of gold to it. And that alloy will not only turn the color of gold, but it'll have the same antioxidation characteristics. So if I take the right alloys that are fairly low cost alloys and add 1 or 2% of gold to them, that pin, and then put a really, really thin plate around the copper of the pin, it will look gold, just like all your USB connectors and all the different computer connectors you guys play with, right? They'll all look like they're gold, but they're actually, they've got just a few molecules of gold in there. Now, if you think about all of the computers and all the laptops and all the connectors to all the iPhones and all the rest that all look like they have little gold connectors, man, you scrape all that gold off, that's got to be a big mountain. Huge mountain. Man, that's got to be a lot of gold. Somewhere I've heard it said, and I don't remember the actual dimensions, but they know how much gold is in planet Earth. And it would fit in a cube that's, I forget, it's, several hundred yards by several hundred yards. It's not nearly like the entire interior being full of iron. It's not that much. So you got to think with all those computers, man, they're going to run out of gold pretty soon. People with my ring, man, well, the truth is it actually doesn't represent much, but it's wonderful in terms of not corroding. So typically all these connectors are going to be crimp type. That's the most common. They do have some where the connector is cast into the housing, or the pin is cast into the housing, and you have to solder it in from the backside. I think I show that here. So in this particular, the pins are all cast and mounted in the plastic of the housing, and then you poke the wire in there, soldering gun up in there, and feed some solder in, and you solder all the wires in. Of course, in a big multi-pin connector, you darn well better make sure you start in the middle and work your way out, or you're going to be in a world of ouch. You're just going to be undoing everything and starting over. Okay? This is the sort of the same thing, RS-232. I think that's like a 15 pin or something. But this shows the same idea, but now I have separate pins that you crimp on, slide in, and they click into place. The tang, the part that locks it into place, in these types, it's usually actually the housing that has a little lock in. And the way to get it to eject with the ejection tool is you come in from the back side of the housing and lift that tang up. In the previous page, and again, there's a bazillion different types of tang, but in the previous page, you'll see here you've got a little tang that comes up, or a little tang that comes up. As that goes in the hole, there's a little latch that the tang then pops up and out of. So you have to come in from the other direction and sort of gently nudge that down to get it to back out. Whatever the mechanism, if it's something that you're going to be using regularly, get the correct extraction tools. Because I assure you, you will put the right pin in the wrong hole at some point if you do this with any regularity. It will happen. And you'll be sad. Okay. Another example of these, of the spring pad type, here's the kind where the wire pin comes in and it wraps around and lays flat against here, and then there's a board that slides in. And this is very much like your USB connector, only much more grandiose. And of course, in here you can see somebody stuck something too big in there and it flattened these guys out big time. These guys still have more than enough spring tension to flex against the board, but somehow or another those guys got mashed flat. So those are going to be intermittent connections, not that good. I will tell you that the preponderance of electrical failures, and I made a lot of money off them. I don't know if it's 90%, but it's up there. They either occur at this end, the pin end of the connector, pin misalignment, corrosion, pin pushback, Like I just fixed a radio that had pin pushback. You know, or out on the other end, the wire breaks off. Okay. Now this one, it's a little hard to see, but it's actually also got a misaligned pin. This pin right here is bent over some. In all likelihood, that connector may work depending on how the female side of the pin is set up. Instead of going in the hole, it may go there and sit on top. Pin misalignment. Of course, when it does that, what's it going to do?
Intermittent.
It's going to work just fine
Yeah.
until it gets nice and far away from you, the mechanic. And then it's going to stop working, and the customer is going to freak out. The first thing they're going to do is, I got ripped off. Okay, now here's the part that really makes a little salt in the wound. You didn't fix it. You didn't have anything to do with that. You had to disconnect that connector to get to something else. But you didn't work on that system at all. When you put it back together, now it suddenly rears its ugly head. And of course, what's it going to do as soon as the customer brings it back to you? You'll start working again. Yeah! These rotten little connectors. So typically, we often will separate the mechanical connection from the electrical connection. So a very common plan form is they create sort of a housing shell with the connector end, the inner shell that holds all the pins, and then out towards the back they have a set of clamp plates. And the clamp plates could actually be internal to the shell, but the set of clamp plates are designed to grab around the entire bundle of wires and squeeze against them, not cuttingly, but it's better to pinch that whole bundle of wire rather than hanging on to one little bitty wire out here. It's also fairly common to take and put a strain relief, some heat shrink wrap or a rubber grommet in there that's also clamped in here. So now with that strain relief, the wire won't work right there. It works over the distance of the strain relief. Okay. Now the two are somewhat separated. Mechanical connection, electrical connection. Obviously, the sky's the limit. Hundreds and hundreds of different types of connectors. You'll see that many of these, the Canons all use pretty positive detent. This looks like about a half-turn thread. So it comes in here, and there'll be some spring loading in there. So the last little bit, it springs down, gets into that detent, and pops back. That can't come undone on its own. Something has to physically grab it and rotate it around, push it in, rotate it around that way, and then start working it out. Bazillions of different kinds. I have no idea how to describe this other than you kind of got to use what it's called for. You also note that they have flange mounts, free flying or free floating, pressure. So you got the flange type or the bulkhead threaded one, kind of like the AN tubing flange connectors. Environmentally controlled ones where they will they allow for pressure differential or are completely sealed so that moisture can't get in. You got to use the right connector, and for some bizarre reason, these are the most expensive things in the world. For example, I've been working with Molex connectors for years, and I recently upgraded to a new type that they've now had out for a few years, their J-type series, which I think are a little bit better connector. For the one size that I tend to use, the 0.62 millimeter size connector, which is good up to about 18 to 19 amps, something like that. There's a set of specialized crimpers for them. They're $290. They're only good for the male pins. The same crimp, but designed for the female pins, is I think $250 or $260. So now I'm 5 yards into this deal, plus a little bit, just to crimp the male and female pins for the one size range. Why that is, I don't know. What I will say, if you buy the high dollar ones, they actually work really well. If you buy the El Cheapos, all they do is crush the connector and make your life very, very frustrating. And that's been pretty universal. So it is important to get the insulation trimmed just right. You want the trimmed lead to go into the part that crimps and not stick just a little bit past. And then just this side of where the part that crimps on the wire leads, there's another crimp that grabs the insulation and wire. So the insulation has to be there. And you don't want it to go in so that it goes in so far that it's actually sticking through the connector. Right? So trimming is going to be very, very critical. You also, no cut strands, only 4 wires nicked. What's a nick? Not much. Okay, don't really define how much it is. So got to be really, really careful there. That's another thing that sort of amazes me. They can build this cool little machine that does wire identification, cutting the wire and stripping the leads and stripping the insulation off appropriately. You program it, and it just throws out thousands of feet of wire a minute. I mean, it's just a whale. Okay, but they can't sell a single set of hand strippers that do the job well in any form, shape, or so a couple of things to be aware of. First off, make sure that anytime you build up a harness or do a repair, check it with an ohm meter and check it with a pole to make sure you're not going to get pin pushback. You also need to note that there's a numbering strategy. For many of these, you'll see we start out and do our circular thing, and in this case, we're going to go this direction, A, B, C, D, A, B, C, D, A, B, C, D, kind of towards the middle, out to the middle. Over here, we have a slightly different structure where we used numeric, and we went 1 feet, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14. So we went up and down and up and down. Most of the time when they're doing linear, particularly with like square connectors, etc., or S232, they never go back and forth. Okay, they always go bada bing, up, bada bing, up, bada bing. Right? Now, okay, hold it to the light, okay, I can just see one of them. Okay, that's 1. So it must go 1, 2, 3, 4, right? Of course, what you're looking at, for some bizarre reason, it says 2 here and 3 there, but 1 is way over here. They do strange stuff like that. Here's the problem. This is the back of the connector. When you come around to the other side of the connector, everything just mirrored on you. Then when you go to the female of the other connector, it mirrored back the other direction. And when you go to the back of it, it mirrored. Okay? See how it can be really easy to get lost. Very, very easy to get lost on this. In general, they're pretty good about embossing the pinouts on both front and back. However, it can be pretty difficult to do, to fit numbers in there. So here you can see they started with a number and ended with a number, but in between the 8, there's 6 unnumbered. So you kind of got to do some counting. And if you're building up that whole harness, and no, building up harnesses like this, it takes days. This is not a quick job. Okay. And also, by the time you're done, do not apply power into it. Make sure you have made the connections. All the wires go in their proper little holes. Otherwise, you will be sad. And the smoke will be happy because it's free. If you go out and play. Yeah, let's stop here.